referred to as AQMF. My name is Nicholas Crouch. I work in the Math Learning Centre. So the first thing I'm going to do is I'm going to point out this book. This one is, we refer to it as Harshbarger and Reynolds, so the authors. This is actually a reasonably good book for this course. It covers almost everything that is in your course. So it's a really good place to look for extra information. Possibly if we're sort of, like we are in sort of about a week or under a week away from the exam, left it too late to read the textbook. But it is a good place to look for some of the information. And it does talk about most of the things you talk about in the same way as your lecturer has been talking about it. So that's actually one of the key parts about this. Got to worry about some of the financial stuff like the annuities and income streams, which you are doing in a different way. Okay? So way you will talk about sort of income streams, annuities and so forth in finance is slightly different from what we're talking about here because we're connecting up to a continuous income stream. And I will talk about that specifically as we get to it. But again, if you need to know the other way of talking about it, come and talk to me up in the drop-in centre because I can explain that to you too. So we're going to cover a few topics. We're talking about looking at things like probability, differentiation, Markov chains, income streams and standard normals. So what we will do, I'm going to take a moment and we will be back with the first topic. Give us. So let's, we've got, again, so like I say, I've downloaded a lot of your notes so that I'm making sure I talk about it in the right terms. But wait, that thing was just annoying. Probability notes. Okay, so when you're talking about probability, what sort of things do we want to know about probability, or do we just want to talk generally? I'll do that in a second. Oh, it's recording. Yes. That's right. Too bad. I mean, they can cut it out afterwards if they really want. So what sort of things do we want to know about probability? So what I'm going to do is I'm going to go through a little bit. When we talk about probability, we're sort of talking about things. We sort of have because of the way like this in general, we have an idea about what probability means. And what we're doing with mathematics is we're sort of formalising. All right, we're sort of putting some notation, some structure on it, so that we have some ideas now. So when we go, they say the Bureau of Meteorology tell you there's an 80% rain. Right? You sort of intuitively know that's like a 4 out of 5 chance that there's going to be rain. All right. And so what they're doing is they've looked over their records, and when the weather chart looks like that, they go, well, 4 out of 5 times it has rain. And so this is a sort of based on experience or observation or other factors, we've come up with this value. So the other thing, so just in terms of the sort of formalities of what I'm doing here, you'll notice that I'm going to make these notes. I'm going to try and keep them A-legible, but they will also be scanned and they'll be put up as a PDF with the revision seminar so that you can download them separately if you want to actually look at them separately. I'm not necessarily sure they're going to be great works of literature, but a lot of people find it helpful to actually have the notes separately. So with probability, we treat it as, so there's, what do they call it? Equiprobable sample space. So if you talk about like dealing cards, So what that term is saying is each So you roll a dice. We assume that everything is each outcome is equally likely. All right. So you've got the values 1 through 6. Any one of them has this, or each of those options has the same probability as coming up, and that's where we base a lot of our things on. So this is where I'm going to go. Take a second or two, just to see. Oh, there you go. So you actually, there's a couple of probability. So what we're going to talk about is things like when we have a set. So you've been using the notation S for sample space. So these are all the things that could happen, right? If I'm rolling a standard six-side die, then I've got the face. The upwards face can have sort of 1, 2, 3, 4, 5, or 6. All right, and so though that my sample space is that 1, 2, 3, 4, 5, 6. When I'm saying they're equally likely, everyone has the same probability as coming up. And sometimes we refer to that as a uniform distribution. You've talked about distribution, so you've seen a normal distribution, you've seen a binomial. When we talk about equiprobable distributions, it's what we call a uniform distribution. All right, and so we'd have this thing where each outcome is the area under that outcome is the same area. All right, so bringing it into, so we wouldn't talk about this when we started talking about it, but this is another way to think about it, and that's saying this sort of represents sort of 1, 2, 3, 4, 5, 6 microphone. Other thing we're supposed to remember when we're doing seminars is to A, put on the microphone, and B, turn on the microphone. Yeah, no, I'm never a fan of hearing my own voice, but I don't have to. Other people have to. So because we know the area is equal to 1, that's saying my total probability. So is equal to 1. Each one of these little bits represents, that's a 6th. Safety goggles. 6, 1 on 6. You get the idea. Okay, so that's one of the basic things that we base our understanding of the things on. Now, when we start talking, so each one of these things we could call an event, but an event can be a grouping of things, all right? So event could be rolling an even number. So 2, 4, 6, and so the probability of even would be equal to number of even on number in the sample space. So the fancy hash we use as we read it as sort of number of, or number of elements in the set. And so in this case it would be like 3 on 6, and we can simplify that down to a half. And so we sort of know that, again, that's a sort of, we know that intuitively, but this is putting a formality on it. And one of the things we like to do with mathematics is we go, because we've taken something which we can observe, and we're sort of formalising it, what we get out of that formalisation should match with what we expect. And if it doesn't, then we ask ourselves, have we observed some phenomena that we wouldn't have noticed otherwise, or have we made a mistake? All right? And it's that question that you should be asking yourself at each step. What do I expect? Does what I've found meet with what I expect? All right? And should I change my expectations, or should I check my working? Okay? And that's sort of that basic underlying idea that we've done it for a reason. We've done it to gain insight. Did I gain insight, or did I make a mistake? So you're going to excuse me while I scroll through some of your notes to make sure that we're... you've used notation, so you would have said your notation, they've used the vertical bars. sometimes they refer to that as the cardinality. So it's important to know the other words that go with this, because other lecturers will use the other terms that are based around this, and it's useful to have heard them before and have at least a basic idea of what they are, so that you can understand until you can get Google to tell you what it is. Coin tosses. Empirical probability. Definition. If a certain event E is observed to occur k times out of a possible n, then we calculate the empirical probability as. So all an empirical probability is doing is saying it is from something observed. So if I'm looking at looking at black caviar, probability black caviar wins as an empirical probability, 26 wins from 26 races, probability they win is 1. Alright? Easy example, because it's only one horse I know. That's not true. About 20 years ago, there was a horse called Rogan Josh that won the Melbourne Cup, and when I was looking through the list of horse names, I'm like, Rogan Josh, got to have money on Rogan Josh. Who doesn't love a good carry? So, but I digress slightly. So the empirical probability is about a probability that we can't necessarily have a theoretical value for, but we can observe based on the information we've been given. Okay? Have no idea about it. So if you were to see, I don't know, if you were looking at the Melbourne Cup and going, if I was to assume that it was an equiprobable distribution, and I'm going, well, there's 24 horses in the Melbourne Cup, the probability I choose a winner is 1 in 24. All right? And so that's where that would be a starting point for my calculation of my probabilities. So yeah. And again, actually one of the other... I'm going to pause. All right. So, poo. My computer's gone to sleep, which has got my notes on it. I hate that bit. Don't you hate it when your computer goes to sleep and you're trying to read from it? So empirical probability is just saying something that we observed. So one of the things that we talk about with a lot of probability stuff is actually the various ways to combine our sets. I'm not going to talk about that. So when we start talking about 2 or more events, so when we're trying to talk about probability of 2 or more events, what we do is we're going to go, hey, let's try and work with that set and sort of bring it back. And we're trying to look at how those things interact. Okay, and so you're going to find we talk a lot about what we call set notation. So we talked a lot about, so if we have A, B, C sets, then we talked about A union B. Or, so that's sometimes said as A or B. So something that is in A or is in B and includes both A and B. So it includes this, and so that brings us to A intersection B. And so this is A and so we say A and B. So I need need it to be in both sets A and B. That helps. I have a little marker here for the bottom of the... Very carefully written, got a little box drawn out on my desk so I can actually know when I'm actually talking off the page. It's just a matter of remembering to look. Yeah, that's what you want. Okay, so these are ways of joining, and so the other one we talk about sometimes is a complement. And so that's why we talk about having a sample space, because that is the everything that we're interested in, and a complement is all the things that are not in A but still in my sample space. All right, you know, like we talk about winning the Melbourne Cup. Well, I'm not going to win the Melbourne Cup because I'm not a horse, so I couldn't be in that sample space. All right, there's no point. So we could get ridiculous and go, hey, you know, this could win the Melbourne Cup. Can't be in the sample. We're not going to talk about it in terms of being in the sample space because it's not the right. Doesn't have the ability to. All right, so. Intersection, complement, and so that's where we get Venn diagrams. So you'll notice that when we do something like this, we'll draw a little Venn diagram. The square represents the sample space, basically. And so we'll have, when we're talking about A and B, and you would have seen your lecturer do this numerous times, I'm sure. Draw a little picture like that. And so when we're talking about A intersection B, so the intersection, just this little bit that's in both sets. Okay? And so we like the Venn diagrams because they're a very useful useful tool for representing something. So. And we can actually use that to represent our information and help us uncover some of the information, some of the things it is telling us that we haven't picked up on originally. All right, 2 seconds. So we probably should do the last one. Last one should be simpler because I have one circle. All right, that's going to be A, because A complement is everything outside of A, basically. All right. So we love our visual representations. While you guys look at that, I'm going to...
Can this lecture go over 2 hours?
So David has given me 2.5 hours. And I'm here until basically over, like, you know, if we go over that, I can sort of start a new recording.
It's not like
what's that?
It's not like, you know, us. It's not like
Yeah, you know, no, I mean, like, I'm sort of aware that this is your revision time, so your time is valuable at this point in time, but if I'm helping you, then we keep going, if I'm not. All right, we're good with that? Okay, so the next thing your lecture notes talk about is a thing called the inclusion-exclusion principle. All right, so a little bit off the page. There we go. Oh, no, there it is, just under. Should be more down here. Like I say, I'm sure the cleaners are going to love me. So this is actually saying that, like, my number of elements in sort of E union F is equal to the number of elements in E plus the number of elements in F minus the number of elements in E intersection F. All right? Now, so the idea is, if you talk about it from the point of view of your Venn diagram, all right, so you've got your, I'm going to say this is E and this is F. So if we're trying to work out the number of elements in there, All right, we have the number of elements in E, which is going to give me this bit. And then we're going to have the number of elements in F, which is going to get me this bit here. But you'll notice how I've sort of coloured in the intersection twice. And so that's why we've added this amount twice, which is why I'm taking it off once. And so there's a corresponding thing that says probability of E union F is equal to probability of E plus probability of F minus probability of E intersection F. All right, so the reason, going back to the equal probable distribution thing, if it's the number of elements is this thing, then the probability follow the same rule. Okay, that's one of those things where we're implicitly exploiting that idea that because we know that the number of elements does this, we know that the probabilities must do the same thing. Okay. And in a similar way, we've got this probability of A complement is 1 minus probability of A. So in terms of sort of the elements of the set, we might sort of go number of elements in A complement is equal to number of elements in our sample space minus the number of elements in A. All right. So we've got sort of these, again, connecting that idea with the number of elements in a particular set with the probability associated with that set as an event. And we love the idea that all probabilities sum to 1. Okay? So, and part of what probability is counting. We go through clever processes to count the number of ways a certain thing can happen. All right? How many ways can I get a pair of cards? Have we thought about this? Let's try this. Probability. So if I'm going to get 2 cards, all right, have we thought about the number of pairs that there is? If I'm going to, have you guys ever played Texas Hold'em? Yep, go. All right, beautiful. Good. So, well, I'm going to get my deck of cards and we're going to play some poker. The plan is I'm going to deal you 2 cards. The probability that those 2 same number, ace, ace, king, king, queen, queen, 9, 9, whatever. We've actually, like if we look at the total number of ways of getting 2 cards, all right, probability, so number 2 cards. Because I don't put the card back into the deck, all right, clearly taken it away, the probability for that first card has got to be 52 times by 51. This is a big number. Off the top of my head, I don't know what it is, so I'm going to ignore that detail. All right, but it's a big number. If I want probability, if I want the number of pairs, all right. Now, so if I think about this, that first card can be any card I like, any one of 52 cards, can't it? Alright? But there is only, if I talk about let's pretend it was an ace, ace of hearts. Everyone loves ace. Then there are only 3 other aces left in the pack. Alright? And so the number of cards that would make this a pair would be 3. Fair enough? So when I get probability of pair, it would be my 52 times by 3 divided by 52 times by 51. I was having a bit of a panic attack for a second there, going, this mightn't work out very well. Because that's one of the other things that happens when I make stuff up as I go along. But we'll see my 52 cancels, and I've got like 3 on 51, which is conveniently 1 in 17. Fair enough? Alright, so we can use our probability to, we can use just that simple counting argument, alright? How am I going to do this? To get ourselves an answer for some of these questions. And like I said, I was a little bit worried about it. I'm going to sort of move on a little bit. So the probability of any 2 cards, so well, the number of different combinations of 2 cards I've got. The first card is a choice of 52 cards, because there are 52 cards in the deck. We assume when we talk about this, we exclude the jokers. The jokers are like a card that they give you, so that when you lose a card, you can write the number on it, and so you know what you can completely get the cards again. So I have my 52 cards. All right. So that first card can be any one of those 52. When I talk about the next card, there is only 51 cards left in my deck of cards, and so there are only 51 options left. But first, any choice for this one, any choice for this one, any choice, any subsequent.
So any 2 cards at all?
Any
Not like, we're not looking for here, we just want
any 2 cards. So my sample space, because when I'm talking about what's the probability of getting a pair, my sample space is the number of possible pairs there are, number of possible lots of 2 cards. Okay? So possibly, actually, that's possibly where we're at is the discussion of what is the sample, how we work to decide on the sample space. We were talking about receiving just 2 cards, so the number of different ways of getting just 2 cards is that 52 times 51.
And the 52 times 3 is?
The 52 times 3 is because that first card can be any card. It doesn't matter which card I get. There is only 3 cards left in the deck that will complete the pair. All right, it doesn't matter what card I got. There are 3 cards left that will complete the pair, and so it will always be sort of 3. And so I can say with reasonable confidence that the probability of being dealt a pair is 1 in 17.
What if there's we just write 30, 51, 51, because think about it's pretty logical, like there's 51 cards, I'm looking for 3 cards. So
Yes.
Yeah, we lose cards.
Yeah, you could go through that process. I would go, one of the things I'm a big fan of is spelling out the whole story, because there may be some part of that where you, like, I didn't actually have any idea what it was going to be when I thought about this. I was just going, hey, that sounds like an interesting thing, let's try and work it out. I'm sure I can. And so I spelled out the whole story, so that, and then when I put it together, I've gone, oh, these bits cancel, and so on. So it actually turns out to be quite a simple calculation. All right? But you don't want to assume it's going to be a simple calculation. You want to go through and do the actual calculation and make sure you've got the information correct. Yeah? So there is a way of expressing everything in a Venn each area in a Venn diagram as an intersection. All right. So I'm going to do. It sort of applies for a three set circle, but if we look at this, this is like A intersection B. This bit here is going to be A intersection of B complement. All right, and in a similar way, this could be A complement intersection B. And so out here is A complement intersection B complement. And this idea that I can break each bit down into a single intersection, into an intersection of the set or its complement, can be a really useful one. So it allows for what we call, I don't think you've used the term partition. Have you heard the term partition? All right. Sometimes having a group of sets which make up the whole sample space is a really useful way to look at my sample space. All right. And it helps with the calculation of probabilities. So your lecture notes go on a little bit about how to use Venn diagrams to calculate certain things. Do we want to talk about that? Other term? Yeah, no. part of the reason I mentioned this is a useful thing, not strictly speaking in your lecture notes, but it is sort of right next to where your lecture notes are talking about. The other thing, your lecture, a couple of other terms that they use. So the term mutually exclusive, all right? So mutually exclusive literally means that there is no intersection. So if A and B then A intersection B is equal to, you've seen the phi used for the empty set? Fancy Greek letter phi. This is a fancy notation for the empty set, the set with no elements in it. All right. And the thing you'll notice about this is I could express my sample space up here as the union of mutually exclusive sets. Is independent from this one. If I did the intersection of those two sets, I would get the empty set. All right. And that is one of those things where it can be really useful to do this. And as a bit of a side note, probability of the empty set is always equal to 0. And since we're mentioning it, probability of the sample space is always equal to 1. Those are some of the fundamental things that we're putting down on.
What does S mean?
That's it?
Is it P5 or?
Probability of the empty set is equal to 0. Probability of
Oh, the whole set.
yeah. The last thing I'm going to mention is the word mutually exclusive. I'm going to put on the bottom here, or disjoint. All right. So disjoint is another way of saying the same thing as mutually exclusive. They do not share any elements in common. Okay.
So what that means is like there's no Venn diagram. It's just like if you were to draw a Venn diagram, it's two circles.
Two separate circles. Yes. This would be sort of talking about a situation where you've got sort of A and B.
Yeah.
And there's no intersection happening. All right? Yes. And it's a useful thing to do. You'd be surprised how often that comes up. Conditional probabilities. Okay, so I probably should spend it. So you guys have talked about tree diagrams with your conditional probabilities, haven't you? And that might be where we get onto something that's actually going to sort of fit in with what you've done. So conditional probability. So this is probability of A given B. All right, and I'm going to trot down what they've got in the lecture notes here. Probability of A intersection B probability of B. All right. We put in the caveat that the probability of B has got to be greater than 0 because I can't have A occurring given that B is occurring if B doesn't occur, all right? And remember, if the probability of B was 0, then B is never going to occur, all right? So this is read as, so probability of A given that B has occurred. All right, so we read that as the probability of A given that B has occurred. All right, useful to note now. So what is probability? So if we go back to talking about dice, we're saying, well, probability of throwing it rolling a 5 would be 1 in 6. Probability of rolling a sum of 2 dice being, say, 8, would, given, so probability of rolling an 8, there's like, what is it, 6 and 2, 6 and 2, 5 and 3, 4 and 4, and then, so that should be like 5 out of 36 possibility. But if I'm then said, if I already know that one of them is a 5, the only way I can get 8 if I know the first one is a 5. So we could have probability of sum of 2 die equals 8 would be equal to like 5 on 36. Probability of sum equals 8 given that would, because that leaves only one option to make the make up the 8, that's going to give me a 1 in 6 probability. All right. So that's how we might use that. We actually use conditional probabilities quite a lot in sort of everyday life. All right, that's sort of one of the things that we. If you go back to sort of talking about when I know Melbourne Cup is like in a week or two's time, so I'm like going, yeah, the Melbourne Cup is a thing. People care about the Melbourne Cup. It might even be next week actually.
Yes,
Next week.
Tuesday.
A couple of days after your exam, yeah. So I mean, like, but the thing is, you'll find a lot of the probability a horse wins will be given track conditions. All right. So you find if it's a beautiful day like it is here and it's a bit warm, the probability there'll be a favourite or a group of favourites. But if you find it's a cold, wet, miserable day in Melbourne, then the favourite will change because given track conditions. So given muddy track will change the probability. So there is a conditional probability associated with these sort of things. I don't really want to go into a lot of that. Now, so independent events, and that is if I have the probability of A given B is equal to the probability of A, that is A is independent of whether B occurs. So the probability that A given B is equal to the probability of A. What it's saying is the information that B occurs didn't change my understanding of the probability. That's what makes these things independent. Sometimes they say sometimes we specify statistically independent because you might be going, oh, those things sound like they're linked, right? Just because of what's happened. Or just because those things are, right, there is some dependence of this thing on that thing. But if the numbers say that my probability didn't change given that this thing has occurred, then we're going, well, actually, statistically, they're independent. All right? So it's saying, based purely on the numbers. And so what we're going to do is we're going, well, this is one way to talk about it. But if we look at this conditional probability idea up here, because we're saying this thing is P of A, we're going P of A is equal to probability of A intersection B on the probability of B if A and B independent. So I can say probability of A intersection B is equal to probability of A plus probability of B. Not plus, times. Times. Multiply. Beautiful. Whoop. Damn. Alright. So, if my events are statistically independent, then I know the probability of the intersection is going to be the product of the probabilities. Okay. So I'm just going to do one last thing on this probability bit to try and put it together, okay? So with my tree diagram, what we're doing is we're sort of listing, because if we're assuming that A and B have conditional probabilities, and strictly speaking, so if I know A and B independent, tree diagram not necessarily a useful thing. But if they're not independent, if there is some dependency on A and B, then my tree diagram is going to be a way to visually represent those conditional probabilities, all right? So this would be B and B complement, B, B complement. And so what we get down here is A complement intersection B complement. This is A complement intersection B. This is A intersection B complement and A intersection B. So if we go back a step, so if I try and put this, all right. So you can see here where I was talking about in the Venn diagram, I can represent each region as an intersection. This tree diagram is another way of representing each of those things independently. And so my tree when I've got conditional probabilities, my first thought is I'm going to try and do this with a tree diagram, all right? Because it's a way of incorporating all of that information into one diagram that's going to help me calculate. And if I want to calculate probability, I just multiply the probabilities along, multiply the probability of A, all right? So I get a probability here, I get a probability here. Because the probability of B occurring, given that A has occurred, we should know from the information we've been given. Okay? We're good with that? Okay. Are we good to move on with the probability stuff? Yep, beautiful, because I think that's enough. Possibly, actually, I'm going to digress for a second. Yeah. I'm going to talk about Markov chain sort of follows on from probabilities. And so I've got a couple of examples on Markov chain that I'm going to work through. So I'm going to put a 4 up here so I know what I'm talking about. So what you're saying with your Markov chains is this process where we've got sort of Vn is equal to Vn minus 1 times P, where these V's are a probability vector. Okay. Apologies for those listening at home. Just drop the microphone. So what we've got is this situation which gives us information about changing states. All right. So probability a woman who used a credit card last month will use the credit use it again this month with probability 0.8. So my wife goes out and buys something with her credit card at David Jones this month. There's an 80% chance she's going to be back at David Jones next month buying something with a credit card. However, we know that the other thing we've observed is the probability that she didn't buy something this month means that next month the probability she does buy something is going to be 0.7. Okay? So we've observed, these are empirical probabilities. This is what we've observed based on past history. And so what we want to do is we want to create P. So we want to find P, the transition matrix. Now, I'm going to be honest, I always have lots of trouble with this. Alright? So what I do when I'm doing this is I go through and I sort of go, well, I know I've got two states. Use credit card, did not use credit card. All right, so my Vn looks like used, not used. All right? And that represents the probabilities for this month, or for the nth month. Okay? Now, I'm inclined to just go, well, let's P is some matrix. A, B, C, D. Now, these represents probability I transition from one state to the next. Okay? So, and so what we're going to do is, if we talk about if I talk about my used in the nth month and my not used in the nth month, that should be equal to the used in the nth minus 1 month times the not used in the nth minus 1 times by this matrix P, my transition matrix, A, B, C, D. Okay. And so how we're going to do this is, how I like to do this is I'm going to just expand it out and relate it to the conditional information I've been given. All right? So when I look at used in the nth month, it should be A times used in the nth minus 1 month plus C times the not used in the nth minus 1 month, so the previous month. All right, so this is just expanding out what this equation means. So this element is sort of this times this plus this times this, just matrix multiplication. And so similarly would be B times.
Is it always as well from
What's
to, so like on the left hand side of your matrix, so like
so the way you guys are going to do this?
AC is like from and it's 2 is B, A, B.
Yeah, so this is the thing. I've read up, you know what I'm talking about, but I'm going to go through this a little bit slowly, all right? Because where those aim, it's useful to sort of have a format plan for working out where they are,
Yeah.
all right? Because if you look, A is the proportion that goes with I used it this month, and so I'm going to use it next month.
Yeah.
And so I'm going to take that from the so I'm going to be able to read that number off from the information above. The C is not strictly there in the information I've been given. Not explicitly, but it is implicitly there. Because we are told they didn't use it this month and will not use it, so probability of not using it next month, given that we didn't use it this month, is 0.7. So the probability I do use it next month, given I didn't use it this month, is actually 0.3, because the probabilities have got a sum to 1. And there are only those two options. Those are mutually exclusive options, either did or didn't. And there's that mutually exclusive idea coming in, all right? My whole sample space is broken into two options, I did or I didn't. And so this is plus D by N, N minus 1. So what we're saying here is this A, I'm going to slide down a little bit, we point out here this lady used her credit card 1 month, with probability she'll use it again in the next month. So A represents that probability of 0.8. And so this is going from the question, we're going to go A is equal to 0.8. Now, the probability that she used it, the probability she's not going to use it next month, given that she did use it this month, based on this, because my probabilities have got a sum to 1, that probability is going to be 0.2. So that's going to tell me that B is equal to 0.2. And so that's from this information I've got this one and this one. Yeah, A, B, beautiful, good. And so from the information I've got that D is equal to 0.7, and so C is going to be equal to 0.3. And so I'm going to put that into my matrix P is equal to 0.8, B is 0.2, C is 0.3, and D is 0.7. And so this has created myself a transition matrix. So probability I start in state A and stay in state A is this. Probability I start in state A and move to state B is this number. All right, and so this covers all the possibilities of started in state A. So this is where the row represents the start state and the column represents the end state. So row state, column, end state. Okay? So, now, so this is just about calculating our probability vector. Okay, we're following this plan. So the row says, so if I look at the row, if I look at this element, it's in the first row, so I started in row 1, I used my credit card. The probability I'm going to use it next month is going to be, because it's in the first column, it's going to be 0.8. Probability I used it this month but didn't use it next month is 0.2. Okay? So, what we're going to do is we're going to imagine that we're going to ask about February next year. Do we think that my wife's going to use her credit card in February next year? You go, no idea, Nick. I know the woman. All right, we're saying my wife just because it's a theoretical person that I can talk about with confidence. So the thing I do know is that December is the month of Christmas, and that will happen. All right, we could have other information, and December, the probability she uses her credit card is 1. All right, and so that means my vector for December, and I'm going to call that 0. My V0 is going to be 1, 0. I know the probability distribution for that month. Okay? So if I want to work out V1, well, that should be V0 times by P. Beautiful. So I should be able to do this. That should be like 1, 0, 0.8, 0.2, 0.3, 0.7. And so we're going to see that I'm going to be able to get, this is going to be 0.8 times 1 plus 0 times 0.8, 0.3. 0.8 for that component, and then 0.2. So this is a probability vector. My V0 is a probability vector. My V1 is also a probability vector. And the beautiful part about my transition matrix is, if I start with a probability vector, I will get a probability vector. Okay, I can be confident by the way because the row sums are 1, I can be confident that if I start with the probability vector, where the sum of the components is 1, I will end up with 1. And so this is my distribution. So the probability she uses her credit card in January is 0.8. Probability she doesn't is 0.2. Seems reasonable, you know. V2. So V2 should be V1 times P. And so in this case, it's going to be 0.8, 0.2, and then 0.8, 0.3, 0.2, 0.7, and so this number is going to be 0.8 times by 0.8 plus 0.2 times by 0.3, and my second component will be 0.8 times by 0.2 plus 0.2 times by 0.7. So it's going to be 0.64 plus 0.06 and 0.16 plus 0.14. Am I still getting that? Beautiful. So that's going to be 0.7 and 0.3. That's amusing. So, next thing that goes with probability vectors, all right, is this notion of steady state. All right, so I'm going to start a new page. That's 4. I'm going to put 5 up here. Okay, so if I had a steady state vector V such that V is equal to V times P. All right. The point about the steady state vector is the transitioning from one state to the next doesn't change my steady state. The state is steady. All right. So with our credit card, what we're saying is my probabilities sort of fall into a steady distribution. Okay. Now, with what you guys are doing, all right, for higher level maths, there are better ways to do this, okay? I'm going to be blunt. There are better ways to do this. But because we're not up to that bit and we don't want to have to teach you the interceding mathematics, all right? And it is, so there's clever, you know, plan, right? This plan involves doing the same things as what I'm about to do, but this is has a simpler explanation for what's happening, okay? So it's basically the same steps, but in with different reasoning, all right? Behind what's going on. So I'm going to put down, so if we have, I'm going to refer to this as my U and my N. I'm going to drop out the little bits is equal to U times U and N times by 0.8, 0.2, 0.3, 0.7. Okay? Now, mathematicians have this thing about making things equal to 0. All right? So if I put this vector over the other side of the equation and write this as UN by my matrix 0.8, 0.2, 0.3, 0.7 minus UN is equal to 0. Strictly speaking, that's a 0 vector. Then what I can do, we know about the identity matrix, don't we? We're going to do a clever little trick. I'm going to times this by the identity matrix. And you're going, of course you are, Nick. Why would you do that? Now, the reason I do think, so this is like timesing by 1, okay? I'm going to do this so I can sort of times by 1. And that is so that when I get to this bit, I can factorize. And I can put my U and my N here. And I can have sort of 0.8, my matrix 0.8, 0.2, 0.3, 0.7, minus 1, 0, 0, 1. And I'm going to make that equal to 0, 0. And so I'm going to have U times N by the matrix. Now the reason I want to do this is going to be nice. I'm going to have 0.8 take 1. And so that's going to be minus 0.2, 0.2, 0.3. So 0.2 take 0, 0.3 take 0, 0.7 take 1 is going to be minus 0.3. Got to be equal to 0, 0. All right. Now, we've deliberately set this up because I don't want U and V. I want this vector, I want sort of, in the background, V is a, V which is equal to our U and our N, so is a probability vector, so U plus N is going to be equal to 1. Okay? That's one of those things we're aiming for. Okay, so I'm going to just expand this out, all right? And so I'm going to have minus 0.2 by U plus 0.2 by N is going to be equal to 0, and 0.3 by U minus 0.2 by 0.3 by N is going to be equal to 0. And the thing we're going to notice about this, right? If I was to divide this one through by minus 0.2 and this one through by 0.3, so divide by minus 0.2, that would get me U minus N is equal to 0. And if I divide by 0.3, that will get me U minus N is equal to 0. They're giving me effectively the same equation. Okay? This is one of those things, particularly for a 2x2 Markov chain system. If I've done this right, I'm going to have this thing happening where those two equations are effectively the same equation. And so what this is saying is my u is equal to n. All right? But u plus n is equal to 1, which would be the same as saying 2u is equal to 1, or u is equal to a half. My n is equal to a half. And so my steady state vector is equal to a half. Do we love it? Yeah, I know. You're going, is that right? But apparently that's right. And when you look at it, because my probabilities of using my credit card again, if I've used it, is similar to the probability that if I didn't use it, I don't use it the next month. That sort of doesn't seem unreasonable. I personally was expecting a slight skewing of the things, but I was like, no, actually that's not far away from what I was expecting. I'm going to accept that as a reasonable answer. All right? And it's calculating that steady state vector. Okay. Now, beg your pardon?
Sorry, can we do a harder example?
I'm tempted to say no. Okay? I've actually got another example which is slightly harder, and so if you want, I'll do that, but we'll take that under advisement because my expectation isn't that we are going to need to be able to do this for a 3x3 system. Okay? So that is about the level of complexity I would expect for the exam. I'm quite happy to do a harder example. I have had, if you'll notice very carefully, I have another example prepared. And so I'm just sort of, what have I got? I've got at least, like an hour and a quarter basically on the clock. So I'm quite happy to do it. And that will, yeah, actually I reckon I might move a bit quicker though. Okay, so what we've got here is we have my friend Pete. My friend Pete was a winemaker. And he earned a lot of money, I don't mean a lot of money, making wine all over the world. He would do this thing where during sort of in the coming months, he would fly into Australia, go to somewhere like Hunter Valley or the Barossa or whatever, and he would work like a demon for 4 months making wine. And then he would get a call from Spain going, "Ooh, vintage is starting soon. How soon can you be here?" And he was like, "I'll hop on a plane." And then he would do a thing where he'd go to South America. And he flew around the world a couple of times a year making wine in different parts of the world. And he's very good at making wine. One of the things that he's done though is he's bought his cars. He likes his cars. All right, he's got this cute little red Audi Quattro. No, seriously. If you got a weak heart, you don't want to go driving with him. All right. So, about the only other thing I noticed about Pete is he doesn't drive the same car 2 days in a row. All right. So, this is a hypothetical question made up based on a similar sort of notion. Okay. All right. So what I've done is I've sort of gone, okay, he's got his 3 cars: his Audi, his Ford, and his VW. All right. So he doesn't drive his car 2 days in a row. All right. So when we're forming our transition matrix, so we're going to have my state vector is going to be A, F, and V. And so what I've done, so in fairness, I've copied this question from a book. All right, make no doubt about it. I think that's this is another one straight from Harshbarger and Reynolds. But it's sort of, that thing where you go, that sounds so much like my friend, it's ridiculous. I will pretend. So what we've got is, so we've actually, this bit here never drives the same car twice.
So I guess that's going to make it obvious that Ford before, like in your from 2 is going to be 0. So it's
From
here.
exactly. So this is implicit information. Now, one of the things that I'm going to keep on going on about you with is that we're trying to interpret the information. All right. Google is trying to make sure that computers can interpret information, but the fact is, even now, computers can't interpret information as well as a human. All right. The best computer in the world doesn't do as well as sort of a fairly uneducated human. All right. And so once you put a little bit of education in them, human craps all over them. All right. But you're sort of going, the probability of going from A to A equals 0. And similarly from F to F is 0. And so my transition matrix has got that zeros along the main diagonal. Now, you notice how I've said my probability of going forward after Audi is 0.7, VW after Audi is 0.3. What we're doing though is we're going to go, we don't actually need this section of information, all right? This extra bit of information over here is actually redundant because we know my row sums have to be 1. We know there's a 0 in a specific spot. Once we put in one other value in that row, we can know that it's, because it's a probability vector, it's got to sum to 1. And you'll notice each through here, that sums to 1, that sums to 1, that sums to 1. Okay? And so remember, our row tells us the state we are, our state we're in, state we start in. The column tells me the state that I'm ending in. So my transition matrix, P, for this situation, so we've got sort of Audi, Ford, VW, Audi, Ford, VW. So I should have a 0 here, a 0 here, and a 0 here. So I want to have Ford after Audi. So Audi is where I started, Ford is where I finished, and so that's going to be my 0.7. Because this is a probability vector along the row, that's going to be 0.3. And VW after Audi, 0.3. So Audi after a Ford down here is 0.6. This one has got to be 0.4. Audi after VW, so after this one, it's got to be 0.8 and 0.2. Okay, oh beautiful. Yes?
Does it matter which way you put it around?
Yes, yes, it really does.
Okay.
Vitally important. Yeah. And part of the reason I'm making that point is because that is one of the things, like I said, there is other ways to do Markov chains, and they will, the transition matrix that someone else, like if I gave this to one of the lecturers in the math department, he would come up with a different transition matrix from what you would come up with. No, we're not going to do it. No, we are not going to. I'm pointing out that if you see something that doesn't fit with your understanding, it may be that because you've done it in one way and the other people have done it another way, and it just requires asking more questions about how they've done it. Okay, we do it this way because I believe this is the way you will see it in a finance world later on. Okay, or moreover, your lecturer, because I'm not your lecturer. And so this has got our transition matrix, right? The transition matrix. If he drove a Ford today, what was the probability he will drive? What is the probability for the cars he will drive in 2 days? So the information he drove a Ford today is saying V is equal to 0, 1, 0. I'm going to call that V0. All right, because V0 is today. And so my V1 is equal to V0 times by 0, 1, 0 by my probability matrix 0, 0.7, 0.3, 0.6, 0, 0.4, 0.8, 0.2, 0. And so across the row, down the column. And so we're actually going to pick out this middle row. This is going to go 0, 0. So that's just wrong. My bad. 0.6. Start with the first row, first column. When I go for he drove a Ford today, when you start looking at the probability he drove a Ford tomorrow, you'll see that I get 0, 0, 0. So our matrix is incorporating that information that if he drove one car today, he's not driving it tomorrow. And then it's going to get me sort of 0.40, 0.4. And again, we're preserving that idea of having a probability vector. All right, so my sum of my elements is still 1. Okay. So, are we good with that? Moving on. I'm going to need that so I can read off the stuff. So, I actually want to find this V2, which should be V1 by P, which would be 0.6, 0.4 times by 0, 0, 0, was it 0.3, 0.7, 0.3, 0.6, 0.4, 0.2. Okay, and so, doing this again, 0 plus 0, 0.4 times 0.8 is 0.32. So this is 0.42 plus 0 plus 0.08. 0.42, 0.08, 0.5. And if I was really lazy, I could just go, hey, what number makes it up to 1? But I will actually go 0.3 times 0.6 is 0.18 plus 0 plus 0. Hey, 0.18 is, and again, I do a quick check. 0.32 plus 0.18 is 0.5 plus 0.5 gives me 1. This is still a probability vector. I have probably got this right. Okay? So that is my probabilities. So if you drove a Ford today, what's that? On Thursday, probability that he's driving a Ford will be 0.5. All right, likes his Ford. It's like, strictly speaking, it's Mustang, but we're gonna. So the drove a Ford. If he drove a Ford, what is the probability that he would drive it in 4 days' time? Yeah. So this is sort of, that was part B. Part C. What I want to find is V4. All right. And that should be equal to V3 times P. But V3 should be V2 times P, which I could write as V1 times P times P times P, which would be V0 times P to the 4. Are we loving that? We've seen this before, yeah? All right. So, okay. Doing this to the power 4, not necessarily a thing. All right? Because it sounds like a bit of pain. I'm going to see if I quickly got something I can do matrix multiplication in. Actually, I wonder if I can do it here. I wonder if it's going to do it for me. Ideally, I should be able to fire up. Oh, hey, you've got a graphs calculator. So, to be. Going to do it for me. Is it going to happen? What's that? So that wouldn't be. So, and the other thing to bear in mind is we wouldn't expect you to do something like that in an exam. Yeah, I was sort of hoping I had something that I could do the calculation in simply. Okay. I wonder if this is going to bring up MATLAB for me. Because, no, I'd have to go through that. Too much like hard work. Have you got the answer there on the graphics calculator for me? Alright. So we're just going to copy it from someone's graphics calculator. So my p to the 4 would be 0.4884, 0.226. Actually, can I put that? No, it's not going to show up. All right, big. 64.2852, 0.3928, 0.37, 0.2737, 0.2968, 0.4664, 0.2368. Okay, so the advantage of having this in here, because my V4 should be equal to, we started off driving a Ford, so we're starting with that V0 times by p to the power 4. This thing is actually going to pick out this middle row. Right? This is a clever way of picking out that middle row, and so that probability is 0.3928, 0.37 and 0.237. Okay, so this is, you don't get graphics calculators in the exam, so they won't ask you to do this. They may give you the power of matrix, alright, but you want to remember this piece of information, alright, and we can summarize that by saying that Vn is equal to V0 p to the power n, okay? That is one of the pieces of information they wanted you to come away with, okay? What is the steady state vector? So this next bit, finding the steady state vector for this bit, we're actually going to jump down to the thing we did there, which was our V by P minus I is equal to 0, the 0 vector. And so what we're getting here is we're getting like AFV by, so because of this, this is going to get me minus 1, 0.7, 0.3, 0.6, minus 1, 0.4, 0.8, 0.2 and minus 1 is going to be equal to 0, 0, 0. So what we do is we expand out each of these. This is not going to be a lot of fun. All right, I'll do it for you, and I'll try and be quick about it. But the way these numbers fall is not going to be, it's not going to make this quick and easy. All right, so that first equation, if we look at that first component, is going to be minus a plus 0.7f plus 0.6. That times that, that times that. 0.8v is equal to 0. 0.7a minus f minus, just in case anyone trying to read it.
Is the case always where you can just do away with one of the equations together and then basically put the constraint that all has to be?
So this is, because we've gone up a degree of complexity, this is not going to quite, so we will, right? So part of the way we've set up the transition matrix means, and this part, this process of finding the steady state matrix, between those two things, means that I can guarantee I will find AV, all right? And that one of those equations will be a combination of the other two. But it is not as simple as just sort of going, oh, it's going to be. All right, so it's 0.8a plus 0.2f minus v is equal to 0. So what I can do is I can say, rearrange this other one to say v is equal to 0.8a plus 0.2f. And by putting that into these other two equations, so I should be able to go minus a, so this equation here is going to go minus a plus 0.6f plus 0.8 by 0.8a plus 0.2f. So expanding and simplifying, so I've got minus a plus 0.64a, so this is going to be minus 0.36a, and this is going to be 0.6 plus 0.16, so it's going to be, alright, I'm going to pretend, plus 0.76f. I reserve the right to make algebraic errors at this point in time. I might write this other one in a different colour just so I can sort of help keep my head clear. So 0.7a minus f plus 0.2 by 0.8a plus 0.2f. And so I should have 0.7 plus 0.16, so this should be 0.86a. And this is going to be 1 minus, so 0.96f. That should be a minus. All right. So, one of the other things that I'm going to do here, because these numbers don't like me, all right, I tried to be nice to them and stuff. So these are equations, and so once they become just equations, I can multiply through by numbers. Okay? So specifically, what I'm going to do two things. I'm going to multiply through by 100, so these are whole numbers. So I'm going to end up with minus 36a plus 76f is equal to 0, and 86a minus 96f is equal to 0. And then, so times by 100. This one I'm going to divide through by 4. I'm going to pick on 4 because 4 looks like a good option. So that's like minus 9a. This is going to be plus 19f. It's got to be equal to 0. And so I can rearrange that one to give me 9a is equal to 19f. None of those are happy. What the hell? Or I might say a is equal to 19 on 9f. And so if I pick this, so notice how I use this top equation to get me this equation, this information, this relationship between a and f. I don't want to use that again. I have to use this other equation. So I'm going to go 86 times by 19 on 9 times by f minus 96. F is going to be equal to 0. And bearing in mind, one of the other things that we're dealing with at this point in time is we've got like a plus f plus v is going to be equal to 1. So I've got this other thing that's going to allow me to work out what they're equal to. No idea. Let's go. So I should have 86 times by 19 divided by 9 plus 96 f. Did I really do that? Oh no. So I've made a mistake. I'm gonna abandon this at this point in time because I've made a mistake in doing this calculation somewhere. I may pause momentarily just to make sure haven't done something silly like write this down wrong. But this equation and this equation should be saying the same thing. All right, that is one of those things where I've gone in doing. So I've rearranged to say v is equal to this. When I put it into here, all right, I must have made a mistake. So I've said a 6.8. And one of these ones, so it should mean this, this, and this. So that one should have been a 3. Good. I should have done that times that times that. That works for me. And just check this one. That's good. Oh, bugger. Yeah, pause momentarily. I should have been able to do, this should be wrong, but I should have 0.3a plus 0.4f minus v is equal to 0, so v is equal to 0.3a plus 0.4f. Much better. And so when I put this into, say, that first one, minus a plus 0.7, no, 0.6, 0.7 f plus 0.8 times by 0.3a plus 0.4 f is equal to 0. So this should have been, so this is 0.24, so this should be minus 0.76a. 0.7 plus 0.32 should be plus 1.02 f. Not happy. I was hoping that was going to be better, but it's still, and that's going to be equal to 0, and so I should have 0.76a is equal to 1.02 f. Yeah. If I do the same thing for this equation, so 0.7a minus f plus 0.2 by 0.3a plus 0.4 f is equal to 0, then I'm going to get 0.7 plus 0.06, so 0.76a, and this, I stuffed that up. I did it again, didn't I? That one should be 0.6. That should be 0.92. Yeah, 0.92. Sweet. It's going to work, you watch. So this is 1, and this is 0.08, and so this is 1, so this is going to be minus 0.92f is equal to 0, and so that's going to rearrange to get me 0.76a is equal to 0.92f. So far so good, right? I can see you going, no, not really, Nick. But that's okay. So we have these two related in this way. And so when we went back to v is equal to this, what was that number? 38. No, that's not going to help. I will do this. I can do my a plus f plus v is equal to 1, and v is equal to 1 minus a minus f, which is equal to, so v is equal to 0.3a plus 0.4f, but it's also equal to 1 minus a minus f, and so I should be able to go put that into there, so 0.3a plus 0.4f, and so 1 is equal to, great. So this should be 1.3a plus 1.4f, sweet. And then
I confused myself.
19, it's not going to work. It's just, these are not nice numbers. All right. I mean, like, ideally, I'm going to go 1 is equal to 1.3 times by 92 on 76 f plus 1.4 f number. All right. I'm going to let that go because I think at this point in time, we can see that it would work my point when I started this process was that it was going to be that it is too difficult to do that size in the exam. All right, and if I just take any arbitrary example, it's just not going to work nicely. All right, but that covers the key points about Markov chains. Creating the transition matrix is actually the most important part. Okay, there is a concept called regular. So for me to be able to find a steady state vector, the matrix actually needs to be what they call regular, which is that there is a power of it so that each entry is non-zero. And that if you're going to get into it, technically it means that they're not what they call absorbing states. Okay? But all you need to know is if they ask you to find the steady state vector, you go, assume the matrix P is regular. All right? And that will cover you for being able to do this. Okay, so income streams. I've got half an hour. I've got more than half an hour. What are we worried about?
Just have a look in.
I was like, I can sit here for a while. I probably have a family to go to.
Get locked in.
That's the thing I want to do.
That's it.
We have all day. Well, modulo the okay. I need the other one. Where do we talk about? Where do they talk about income streams? Is that in the calculus section?
Sorry?
Is that income
streams that relates to integration.
Yes, that would be at the end.
It's like the very end of integration. And yeah, it's just on some dumb shit over to say it's pretty hectic.
approximate areas? Aha. Try the next one.
I just don't even get it, but yeah, yeah, it's often like a last question in all the exams, which is like on income streams.
Yeah, so this is one of the bigger changes to sort of the discussion to the AQMF course in the recent years. How they've talked about doing income streams and talking about them as doing talking about them as integrals. And in fact, so if you remember back to where you started your discussion on integrals, you talked about them in terms of upper sum and lower sum, the area, finding the area under a curve. So what you've got to do is you've got to imagine your income stream as a curve, right? And so work out the total value of the income stream is you're treating it as finding out that area. The problem with working out that area, right, is that we've heard about the time value of money. You've heard that phrase, yep. And so what we're saying is money in the future is worth less to me than money now. All right? You tell me you're going to pay me $100 in a week's time, I'm going to be less impressed than if you pay me $100 now. All right? So my income devalues over time. And so what we're doing is we're incorporating that function, which represents the income stream, with a depreciation factor, which allows for that. And so you're doing a continuously depreciating factor. That's what's going on. I still haven't found the correct page of lecture notes, and I really would like to make sure I have the correct page of lecture notes. So, average value of function income streams. Let's go down to the bottom of this one. Derivation of future value of income. So the thing about, if we look at what they're saying about an income stream, all right, so for a fixed amount P at present value, the future value S of a blah. Okay, so we're going to do a couple of things. Firstly, like future value of an amount A, we say compounded . So typically we'd say that my future value for an amount, so if I just have my, my $50,000 in the bank, all right, and it's compounded continuously. So compounded continuously is like that continuous devaluation thing. So we, banks deal with discrete compounding, compounding quarterly, monthly, and now I got a letter from the 1 year. There was about maybe 5 or 10 years where it is a tax return, and so I got a nasty letter from the taxation office saying that they were going to fine me the outstanding amount, and they were going to compound it daily. And so I thought to myself, well, this is a bound on how much I owe the taxation department. Let's type that into a thing and work out the compounding continuously, and I named that unblocked. Because it was less than the money it took to write me the nasty letter. Well, less than the amount it took to post the nasty letter telling me that they were going to do it. And then so I thought to myself, all I will do is politely ask them for a daily, since they're compounding daily, ask them to post me a statement of the daily balances. And then I could dispute each one of those, and it would have been worth much less of their time. Do your tax returns on time.
Is compounding, the basic compound continuously is like a limit of, it's like that nominal interest rate. But that's
Yeah, so have you, I'm reluctant to go into the compounding thing too much. Have you talked about that in
it's all to do with limits, isn't it?
You've done the intro to financial maths thing? Yeah. So you would have seen a formula that looks a little bit like, what would it look like? So you would have had your amount, and it would have been like 1 plus I on n to the n times by t. Yep. And so, so the limit as n goes to infinity of this formula, so if I do, so this is my future value, for a discrete number of compounding per year, so t is the number of years, n is the number of compounding periods, I is the interest rate per annum. So I...
So I guess like, yeah.
So if I do like limit n goes to infinity of this future value, limit n goes to infinity of a 1 plus I on n. That's where that you get a e to the it from. Okay? Beg your pardon?
So with AQMF, we only have to worry about the first question.
Yeah, yes, that's why I wasn't going to go into it. All right. But you have seen that stuff before, yeah?
We had to do the first one.
Yep, that's okay. So the point is that this thing here is giving me the future value. And so conversely, if I talk about present value, the thing would be like the future value e to the minus rt. So that's the devaluing of that value. All right?
So, are these questions saying that you have like a certain amount of money in
So
you're letting inflation get to it, or like, or is it saying,
well, so if we talk, it's more.
or are you saying like I want $50,000 in 10 years' time? What's the present value of that?
What is my, so if I know, if I've looked into crystal ball and it tells me I'm going to win $1 million in 2030, how much is that worth to me now?
Yes.
And so that's allowing me to sort of devalue. So, but the reason I'm going on about this at this point, right, is your formula for working out your income stream. So you're talking about, so present value for an income stream is listed as being integral from 0 to, go away, 0 to k of your income stream times by this e to the minus rt with respect to t. Okay? Now the point about this is this bit here represents that devaluing as you go further along. Okay? So sort of at 0, that e to the minus, when t is equal to 0, e to the minus rt is going to be equal to 1. There's no devaluing. But as we go away, it's sort of pushing down that income stream. So if you imagine...
So limit time decay.
Yeah. So the, I mean, like, ideally, the point about what's happening with pay rises, all right? I get a pay rise every, let's say every year. And so what's happening is I've got this income stream that is doing this sort of thing. But once we've allowed for the devaluation of it, this is bringing this back down to a straight line. So if my income, if my income stream goes above that, then the corresponding thing that it does will come sort of, it won't be so high, but it will be an increasing income stream. And so that's what this formula is representing. This is doing the summing of all those possible values. Okay. So that is the key thing. And again, because it's financial maths, we're talking present value, future value. The one thing we really need to be clear on is whether we're talking present value, future value, and sort of from what time frame. So one of their favourite pastimes is to say, you know, in 10 years' time you will need this much money. You know, how much money, how, you know, what pick a point somewhere in between there and try and work out the value at that point. And so it can be quite difficult to sort of judge where you need to do this, all right? So you want to be quite clear at every point in time what, whether you're talking a present value or a future value. Now, so, and possibly that's the other thing is when we're talking our future value, that's like e to the RT integral 0k f of t e to the minus RT, that's a k dt. All right, so this is saying I bring it back, this bit says I bring it back to present value terms, and then I compound it up to the what it would be worth in the future. So this is really going back to the ordinary compounding interest type of idea, where I work out the present, I have a value for the present value, and then I just multiply it by the appropriate factor to get what the future value is based on that.
So what's ft then?
So inside the integral, t is literally acting as time.
Oh no, so you've got ft there. Like, so is that like a? Do we have like a function that goes into?
Yeah. So ft represents an income stream. So the function.
So, yeah.
I'll give it to you.
ft.
Oh right.
Like this is how much you're getting paid as a function of how much you spend.
Yeah. Right. Yeah. Okay.
So one of the examples you had in lectures you had f of t is equal to 15 e to the minus 0.3 t plus 5.
Yeah.
And so, so 5-year period. I suppose money is worth 10% per annum. So that's going R is equal to 0.1. Compounded continuously. So if you wanted to work out, so this thing they're talking about is giving you an income stream. This investment is giving you an income stream, where this describes the income stream. All right, and so this decaying exponential is actually doing sort of, rather than doing this, it's actually doing sort of this. All right, and so my devaluation is actually going to bring it right down. So the present value, my p for this situation. So we're going up with this one. We've integral from 0 to 5 of this, 15 e to the minus 0.3 and then t plus 5 times by e to the minus 0.1 t dt.
When it talks about time, how do you work out whether they're referring to time as t or time as k? They're both like years.
So we've got to be a little bit careful. So k is a fixed value, all right? So in this case, we're talking about a period of 5 years. So that's the fixed 5 years. In this case, my income stream is a function of time, but it's the t because it varies based on the time where you are in that period.
This is just measuring
Yep.
what it could be, and then you can use that to substitute in any
Yep.
So is this like you're going to use substitutions?
No, this is a little bit simpler than that.
Oh, really? So something that's simple. That looks like fucking
It's like a world of pain.
It does.
I
Like,
know. But No, not sleep. So the thing we're going to do, you're faced with something like this and this looks horrible. Okay? So the first thing I'm going to do, I've got a 15 here. I'm going to put the 15 outside because it's a constant. 0 to 5, e to the minus 0.3 t minus 1.5 times e to the minus 0.1 t. When I've got the same base here, I can combine the powers. I can add the powers. And so this is the same as saying 15 integral 0 to 5 e, so I'm going to add these powers, minus 0.3t and minus 0.1t is minus 0.4t minus 1.5 dt. I'm going to shuffle around a little bit. 8. So I'm going to call this one 9, 10. And so with this here, I'm going to see how I sort of combine them two based on the power, and I just added things in the power. I'm actually going to sort of do a little bit of the opposite. E to the minus 0.4t times by e to the minus 1.5. Now, this e to the minus 1.5 is just a number. All right, I think that number is about 5. I don't care really. Oh no, it's about 1.2. I'm going to go with 0.2. All right, I'm prepared to be wrong about that. But so, but because it's constant, so I can put that out the front. Now, strictly speaking, what I should do to work out this integral is I should go, let u is equal to minus 0.4t, and so du is equal to minus 0.4 dt. Okay? Or minus 1 on 0.4 du is equal to dt. And so this integral, 15 times by e to the minus 1.5. I'm going to do a trick. This is because these are values of t is equal to 0 and t is equal to 5. I'm about to transform my integral in terms of u, and that means I should transform my limits of integration in terms of u. So this is going to be e to the u times by minus 1 on 0.4 du. All right. So if t is equal to 0, u is equal to, so if I put in t is equal to 5, minus 0.4 times 5, u is equal to 2. So this integral, 15 times by e to the minus 1.5, integral from 0 to 2, and that's like u is equal to e to the u minus 1 on 0.4 du. And so I can just do this integral now. 15 times by e to the minus 1.5 times by minus 1 on 0.4 e to the u, and this bit is going to be evaluated at 0 and 2. And so I am going to get 15 times by e to the minus 1.5 times by minus 1 on 0.4 times by e to the 2 minus 1. E to the power 0 is 1 number. Don't know what that number is, but it's a number. All right, and that would represent the present value of that particular income stream. Yep. Oh, sorry.
Yes.
Just off. Okay. So one of the things I wanted you to notice is with dealing with that. I'm going to try and slow that down just a fraction.
Right, so you've moved the quarter to the front.
Yeah.
And then the EU.
Yes. So because what I'm left with inside the integral is just e to the u.
Yep.
It was e to the u.
And u is equal to 2.
Yep. So I've reevaluated my limit. So when t is equal to 0, u is equal to 0 because it's a constant multiple.
Oh, right. Yeah.
And when t is equal to 5, u is equal to 2.
Right. Nice.
Possibly minus 2.
Right. Okay.
We're going to adjust that and work in a minus here because that should be a minus 2 there. And that should be a minus 2. And that will make my number work better for me. I'm not happy with that number.
Otherwise, it looks like a really bad investment.
Yes. I'm not sure it looks like a great investment as it is. But yeah. So this it should now be a positive investment. So that's that process. The key part about this is working out. We've got that continuously devaluing factor inside an integral. All right, and we're treating it as an integral. I might leave that section there. Someone said I wanted to try some tricky. Do you guys need that up there for a bit longer?
Yeah.
Yep, please. Tricky derivative things. We've got the book here. That's right. Yeah, no, good. Derivatives. We want to do about. I want to do something about 700.
There's too much shit in this course. There really is. It's alright.
Amusingly enough, I was going through it last night, and they've taken a little bit out. They still haven't taken it down, so it's a reasonable course, but they've taken a little bit out.
Yeah, at least we have to work harder than the people in here.
Sorry.
The people that do like finance and media, they work on it. So
Yeah, true.
what's wrong with Shane?
Like, I don't know. I'm actually really gonna miss doing maths. Like,
Yeah, well, you can do a whole maths degree. I did.
yeah, but like, I feel like this is actually just easy maths. It's just back to maths.
I know you can say stuff on the first year engineering.
So honestly, a lot of the guys who are doing a double with engineering and finance, they say that the algebraics, like the mathematical skill you need for a finance degree, really doesn't go much beyond what you have now. All right, and because they've done the extra year of maths, they find it very simple. What you do need with the finance degree is that ability to interpret what's going on. That is actually the key skill that you've got to get. So,
But like, so I guess at the same time that like if, because like, I really like this course. My grades don't really reflect that though. But like, if you wanted to do more maths, like, would this just not be enough for you though, or you know?
oh look, I mean, like from where you are, you probably have to do like I'd get you to talk to the coordinator of first year maths,
Yeah.
and he would sort of tell you about where he thinks you should sort of fit into the course.
Oh yeah, I read in that.
Oh yeah.
That's some school.
So you have limited things that I can throw at you in terms of horrible derivatives. Have you talked about the derivative of natural log?
Yeah, it's one over.
Yeah, so if I do d by dx, whoops, too low. All right, beautiful. D by dx of ln of x, we say that's 1 on x. All right, and the derivative with respect to x of e to the x is just e to the x. All right, so if we do the derivative with respect to x of, say, ln of something horrible, what have we got here that's horrible?
Could we, later on could we do some integration by parts?
We can give it a go. If you do something like that, all right, there is the 1 on x cubed plus 1 on x squared times by the derivative thing in the brackets, and so that would be derivative of the top line, 3x squared times by the bottom line, x squared, minus top line, x cubed plus 1, derivative of bottom line, 2x, bottom line squared, x to the 4. Because I'm dividing by a fraction, x squared on x cubed plus 1 times by x to the 4, and this is going to get me 3x to the 4 minus 2x to the 4 minus 2x. Alright, and so a little bit of this can cancel with this, and that leaves me with 1 and an x squared. Nope, going too low, going too fast.
Oh, so it's more than a fraction.
Going too fast, gotta go.
Yeah, are you going to scan any of this information?
Yeah, everything's going to be scanned and uploaded. I've only got 20 minutes on the recording anyway.
Yeah, because I'm talking.
Yeah, no, that's right. So,
Are you saying that, like, if you did it this way, it's kind of like the overly complicated way, you can give yourself a headache?
you couldn't, yeah, this would be the give yourself a headache sort of way.
And I gave myself a headache doing because I did it this way. Whereas then in the answers it was like, yeah, just divide the ln. And it's like, of course. So like, because inside the ln you've got a fraction, which means it's basically like the top minus the bottom.
Yep. Oops, too far.
You just made your life much easier.
So what it could have done is this one could have been derivative with respect to x of ln of x cubed plus 1 minus ln of x squared, which I possibly would have gone the extra step and gone derivative with respect to x of ln of x cubed plus 1. Because of the plus 1 I can't do anything about it, and I've done that deliberately, but minus 2 ln of x. And so the derivative, so this is going to get me derivative of that, 3x squared on x cubed plus 1 minus 2 on x. And so if you look, I've got a factor of x out of here, so x cubed minus 2 on x cubed plus 1. Alright, and so if I put this over a common denominator, it's going to get me x by x cubed plus 1 as the denominator, and it's going to get me 3x cubed minus 2x cubed plus 1. Going to be the same thing. It's going to get me x cubed minus 2 on, no, I'm still on the page, good. Do I need to move it so you can see part of it?
No, it's
Good. So I can do that process, alright?
Yeah.
The other thing, so that's one part of the doing derivatives of the LNs. Yep,
No, I'm sorry.
that's okay. So that's one aspect of it that.
So like you pretty much always better just split that.
Yep, always.
Yeah.
I'm yet to find a situation where it wasn't the right
So
thing to
good.
do.
Like just honest that is just fucking tearing my hair out.
I didn't know you could do that. You should write down the log rules.
Oh, I just copy
Yes,
all the
log laws.
copy
Yes.
down log laws and just
You should make sure you write the log laws.
sleep on them.
You run out of tissues?
No, I haven't had it. I just.
This is just like such. It's just tier interesting stuff. You know, it's just.
So the other thing that causes a lot of people problems is chain rule. We've got a function inside a function.
Yeah.
So possibly the easier, possibly we will do something like, I will try and keep it, are we good, ready to move on?
We should do some integration by parts as well.
I will try and squeeze, I'll do one more thing with the differentiation. So if I do the derivative with respect to x of, say, square root of x plus 2 on 2x plus 7, alright, so this is derivative with respect to x of this thing, x plus 2 on 2x plus 7 to the power of half. So my chain rule says put the half out the front, x plus 2, 2x plus 7, take 1 from the power, so minus a half, times by the derivative of the thing inside the brackets. And so again, I'm using quotient rule on doing this. 2x plus 7 all squared. With this, I would never actually expand out that denominator. It just makes your life hard. Derivative of the top line is 1 times the bottom line. 2x plus 7 minus derivative of the bottom line, 2x plus 2. Now, so because this is a negative power, I can take the reciprocal. So I can write that as the square root of 2x plus 7 on x plus 2 times by this bit 2x plus 7 to the power 2. This is going to get me 2x, this is going to be minus 2x, so the 2x bit cancels, this is going to get me 7, this is going to get me minus 4, and so I'm going to be left with a 3. So if I really wanted to, I can write this as 3 on 2, and then 2x plus 7 to the power. So there's a half on the top line and a 2. So this is like a half and minus 2. So that's going to get me a 3 on 2 here in the denominator. And this thing, x plus 2 to the power half here. So I could actually write it like that.
Just generally leave it as like
Could you just
how complicated, not simple.
This would probably be alright.
Yeah.
This is sort of like, you know, this is like that's the finishing line, peoples. Integration by parts. So we're happy?
Yeah, that's it.
All right.
So, okay, so I guess is that like, is there an easier way to do that? Or nah, like that's just yuck. Like you just got.
I chose that one because I know that is just plain horrible.
Yeah, it's good though. Hey.
I mean, like, I know I chose that type because I know it's just plain
Pretty
horrible.
juicy.
Yeah, even as a fraction in a thingy is right.
So give us a really hard integration by parts question.
You know what? One of the hardest ones is one of the ones that looks the easiest.
And I'm like, I've just been.
Have you done?
Yes. Yeah.
Yeah, we did that in class.
Damn. That, all right. So so this is where you do the 1, and so you do your f dashed is equal to 1, and so f is equal to x. Your g is equal to ln of x, and so g dashed is equal to 1 on x. You'll forgive me, I almost always write the formula in a different way.
Yeah, no, I like it that way as well. It's way more straightforward.
So it doesn't matter which one you put the dashed on, as long as the other, on the other side it's on the other one.
Right.
All right? But you'll notice how I've set it out, like I've said what f is, I've said what g is. And so I'm going to be clear about what I'm doing, what is each one. And so my integral of ln of x with respect to x is equal to f times g, so it's like x ln x minus the integral of f x times g dashed, 1 on x. This is just 1. So this is like x, so it's like x ln x minus the integral of 1 dx. And so this is x ln x minus x. And we should add a constant of integration because, so probably the next under the heading of difficult but simple. All right, have you seen this one? Damn. So same process. This is going to be f is going to be equal to x. You'll notice I've done exactly the opposite way around because I'm a clever person. And so g is equal to e to the x and f dashed is equal to 1. And so my integral x e to the x is going to be equal to f times g, x e to the x, minus the integral. And so we had this to start off with, so it should be this, e to the x. And so it's x e to the x minus e to the x and plus c because it's constant of integration. What could be more difficult?
See, what they had the exam was really sneaky. It was like 2 ln x squared. So they first made you like put that 2 back up on the x squared to make it x4, and then they made you bring the 4 down and then the linearity. So like unless you kind of saw that, it was like just confusing. You know what I mean?
Yeah. Aside from little tricks about doing these things, I'm not sure what the best thing, what a good example that is actually illustrative. They did an x cubed e to the x, which is a similar sort of thing.
When I was studying lectures was x squared, right? Then times e to the negative 3x. And then
All right.
integrate that by parts.
So the thing about this, so we're talking about doing integral x squared e to the negative 3x. Yep. So we saw before when we had back here when we had like integral of x e to the x, we ended up going one step and we're done. We got an integral we can solve.
Yeah.
When we've got an x squared, we actually need to do two steps.
Yeah.
All right.
Super gross.
So your f is going to be equal to x squared, your f dashed is equal to 2x, your g dashed is equal to e to the minus 3x, your g, so I'm integrating this, so I'm getting minus 1 on 3 e to the minus 3x. And so your integral x squared e minus 3x is going to be equal to f times g, so x squared times minus the third e to the minus 3x integral of, so we did those two to start off with, so it should be those two. 2x minus 2x on 3 e to the minus 3x dx. Now that leaves me with this, which I still need to do integration on by parts on. And so integral minus 2 on 3x e to the minus 3x. Again, it's important that I see how this is like a polynomial bit, the f is the polynomial bit and the g dashed is the exponential bit. It's important that I keep that intact. Minus 2 on 3x.
It's like, what's the rule again? It's called Liact. That's like a little trick I found. This goes logs, inverse trig, algebra, trig, and then exponential. And whatever comes up first, that's the one that turned into your
Oh, yeah. So actually the rule of thumb is you're looking for the thing that's going to make it simpler.
Yeah.
All right. And so if you see a polynomial bit in there, you want to be you want that to be the ordinary function bit, because you differentiate it and it will make it simpler.
Yeah.
All right. If there's an exponential bit in there, and then if there's like exponentials, trigs, logs, right, we can't do the integral of log, so that has to be the bit that we differentiate. So we know there are some things there's sometimes choice. Like in this case, could go either way. One was going to make it more complicated, one was going to make it less complicated, and so that's where I went. I chose the bit that was going to make it less complicated. Sometimes there is only one bit that I can integrate, like that ln. I can't do the integral of ln without doing integration by parts, and so I should go through and do this. So the integral minus 2 on 3x e to the minus 3x is equal to f times g. So minus 2 on 3x times by minus 1 on 3 e to the minus 3x minus the integral of minus 2 on 3 times minus 1 on 3 e to the minus 3x. Man, there is a lot of minuses going on there. So this is going to be like 2x on 9 e to the minus 3x. That one and that one give me a plus. And so this, because this is going to get me, so that's going to be like, it's actually going to work out to be plus 2 on 9 e to the minus 3x. 1 on 3, forgot my 1 on 3 in there. Which are going to go 2x on 9 e to the minus 3x plus 2 on 27 e to the minus 3x. And that goes in here, so my integral x squared e to the minus 3x is equal to, x squared minus x squared on 3 e to the minus 3x minus this 2x on 9 e to the minus 3x plus 2 on 27 e to the minus 3x minus x squared e to the minus 3x on 3 minus 2x on 9 e to the minus 3x minus 2 on 27 e to the minus 3x plus c. Something like that.
So it's like an inception shit up there, isn't it? Like,
Yep.
it's like
You have to, only thing we had to do is apply the rule correctly
Yeah.
and be consistent about the way we've broken down the function. that
Yeah.
we've declared. Okay, I'm actually about out of time, so the recording is about to stop in 5 minutes. So the last thing was doing this normal model thing. 13. So one of the things, you had your normal model, all right? So where you had your mean and had your standard deviation. So you had your rule of thumb. So plus or minus 1 sigma was 68%. Plus or minus 2 sigma was 95.4%. And plus or minus 3 sigma was like 99.7. Actually, I don't know that you talked about the 99.7, but a lot of places do. All right. The thing where, because it's a normal model, it is symmetric around the mean. So and we do a Z transformation, x minus mu on sigma transforms any standard deviation, any normal model into a standard normal model. So the Z corresponds to the normal. Okay. So, all right. So, IQ is, so we say normally distributed, 115.
Yeah.
All right. So, we might have said that the probability of 0 less than or equal to z less than or equal to 2 might well have been, what is it? 0.4775. 7, damn. All right. Going from memory, all right. So, and all right, so roughly speaking, they say people with an IQ less than 70 aren't able to look after themselves. Right? They don't have the ability to look after themselves. We're going, hey, what proportion of people is that? All right, twin. And you're going, so the information I've given is actually enough to do this. Okay? And we should go, hey, we can,
Is that P less than Z less than 2, sorry?
so 0 less than Z less than 2
Oh yeah, sure.
is giving me a p-value. So the first thing I'm going to do is work out my Z. And my Z should be equal to 70 minus 100 on 15, which is going to be minus 30 on 15, which is equal to minus 2. Okay? And so I want people with IQ less than 70. So my picture should look like 100 here. I should have 70 out here. And so I'm actually asking for this probability. My question has told me this. All right, and we're going, what the? Hopefully you are going, no, Nick, I can see exactly what we're supposed to do. So because we've worked out a p-value of -2, a z-score of -2, all right, this area here, because of symmetry, is going to be the same as this area out here. Okay? I'm going to do it in the blue pen.